And this thesis is actually focused on the reviewing experiments and their results. So let's first start with what is this material. Inconel 718 is one of the most popular nickel-based superalloy, and is famous for its excellent mechanical properties like high strength and toughness under high temperature, oxidation resistance, and corrosion resistance, and so on. So this material is widely employed in the aerospace industry, especially for the hot section of the turbine engine. So why we study the drilling of this material? Firstly, because around 75% of material removal process in aerospace industry involves drilling. And then because of the excellent mechanical properties of this material, Inconel 718 is also defined as the difficult to cut material. And this brings a lot of challenges to the manufacturers, and also took a large amount of time, money, and also labor resources. So this is why we want to review the experimental results and try to find out a feasible machining strategy to handle these problems. The reviewed experiments in this study include, firstly, the tool geometry, which is about the different shapes of cutting edge and influences of cutting parameters and their contributions to tool wear and surface quality. Then the vibration test, and finally the influences of cutting fluids. So for the results of tool geometry, we see that we have 5 different shapes of cutting edges. For drill 2, 4, and 5, they have curved cutting edge here and also a rounded corner point. However, for drill 1 and 3, they are straight or concave cutting edge, which lead to sharp corner points. So based on the results, we found that drill 2, 4, and 5 performed much better than drill 1 and 3, and they produce up to 3 times more on cutting length. However, this geometry is not so satisfied for surface roughness. So we see except drill 4, drill 2 and drill 5 produce relatively higher surface roughness compared to drill 1 and 3, and also larger variance on roughness. So we can conclude that although this geometry effectively prevents the tool wear, the slightly sacrifice on the surface roughness. Alright, next we move to cutting parameters. This figure shows the tool wear at different cutting speeds from 10 to 17.5 meters per minute. And we see that the tool wear gradually propagated and also moved from out corner towards to the center of the drill bit. And also the wear became more serious, which is from simply just purely wear to chipping, which just took off a piece of the material. And also from the diagrams of hole diameter and deviation of hole roundness, we find a common trend that the increase in feed rate will increase the deviation of hole roundness and also enlarge the hole diameter. And this is especially obvious at the high cutting speed as showing the purple lines. So we explain it as at high cutting speed and high feed rate, the considerably accelerated. So based on this result and also the previous one, we can see the significance of feed rate and cutting speed to the tool wear and surface quality. And also we can see that the tool wear is actually directly related to the surface quality. Alright, to determine the contributions of feed rate and cutting speed to tool wear and hole quality, we did the calculations of SN ratio and as shown in the response tables. And from table 1, we see that the feed rate is much more effective than cutting speed on tool wear. However, from table 2 and 3, we found cutting speed actually contributes slightly more feed rate on hole quality. Okay, for the vibration, we've already know that vibration have impacts on both tool wear and surface quality, and also vibration is not possible to be eliminated during the machining process. So the only way is to reduce it. So similarly, we did a SN response table, and from this we found that the feed rate is the most effective factor which affect the vibration. This means the feed rate is the most effective factor that can be used to reduce the vibration. And also cutting speed and clamp length are another two factors that may contribute to reduce the vibration. However, the effect from cutting depth is quite limited. Also from the diagrams below, the combined SN ratio diagrams for tool wear and vibration, we see that at higher levels of feed rate and cutting speed, which are referred to A and B, the amplitude of vibration is increased, and simultaneously the values of tool wear increase as well. So from these two diagrams, we conclude that the vibration is directly proportional to the tool wear, as higher vibration amplitudes will lead to a higher tool wear rate. So for cutting fluids, we surprisingly find that the size of nanocrystalline grain is much smaller on the dry cutting conditions than on the wet cutting conditions. And this is explained as at dry cutting conditions, the cutting temperature is much higher, and this leads to an unstable grain structure, and it reduces the size of it. So this suggests that the existence of cutting fluids actually provides no improvement on surface quality. However, by looking at these two diagrams, especially the rack face, we see that the rack face on the wet cutting condition is much smoother than the one on the dry cutting condition. This is because the cutting fluids will lubricate the interface of the tool and the workpiece, and also reduce the cutting forces. So we can see that the existence of cutting fluids do prevent the tool wear. So in conclusion, based on these results, we found that the curved cutting edge with radius on periphery prevent the tool wear effectively, although they increase the surface roughness. Then, if we want to prevent the tool wear and also improve the surface quality, we need to keep the feed rate low and also choose a relatively lower or intermediate cutting speed. Then for vibration, it is directly related to tool wear, and for reducing it, we suggest to reduce the feed rate cutting speed and also increase the clamp length for a more rigid drill bit. And finally, coolant is not suggested to be eliminated currently, although it may produce pollution to environment. So for the future work, the first thing is we need to validate these results by real experiment. And also, high-speed machining technology is really suggested to eliminate the cutting fluids. And the way to achieve this goal is then we need more advanced tools, such as ceramics or even diamonds. And that's all for my presentation. Thank you.
Any questions?
Hi, Yawei. So you presented a lot of figures in the results section.
Yeah.
Are those your work or are they from the literature review? Because you put a lot of citations at the bottom.
Yes, yes. Well, some pictures like the toolware are from the papers. However, some data is discussed and rearranged by myself.
So none of them are actually measured by your current.
No, because I never did the experiment, so yeah,
all these are literature review.
Yes.
Why?
Just to clarify.
Okay. Well, actually, we were preparing for the real experiment, but because of some out of control reasons from the school, so we will notice that the machines are not for research anymore. So yeah, just change the orientation of this building. Yes.
Sorry, how do you get the SN ratio as you mentioned?
SN ratio.
Yeah, so it's for the vibration, I think.
Okay. The SN ratio is actually used to measure like how important this parameter affect to the tool wear and the surface quality in this case. So for this, we firstly calculated the root mean square of the values of each parameter to the tool and the vibration, and based on this root mean squares, we applied equations. There are actually 3 equations for 3 different cases, which are the smaller the better, the larger the better, and also the longer the better. So for example, for the vibration, we want to reduce it, and the vibration is the smaller the better. So we apply the corresponding equation, and then we calculate the SN ratio. Yeah. So any more questions?
Any other questions? No. Okay. Thank you.